Hello and welcome back to Calculus 3. We're starting chapter 12. So this is a new chapter of your life in Calculus 3. So we're talking about planes and surfaces. We already talked about basic planes. We said that the floor we are standing on, we can think of it as XY plane. And that XY plane, the floor, was described as the z equals 0. And if you look at the ceiling, we describe the ceiling as z equals to 10. So we have these parallel planes that are stacked on top of each other, where the one on the bottom is going to be z equals to 0, and then one on the top is z equals to 10, and they are parallel. And you also have the same situation with walls. Y equals 0 and x equals 0 for walls. And then you go whatever amount of feet left and right, that was about 30 feet each way, and you get the walls. So you will have 6 different boundaries to create a box that we are sitting in right now. But the planes can also be skewed in space, so they don't have to be parallel to the default ones. They can be skewed, so we can have in our XY coordinate system, XYZ, we can represent the plane as the intersection with all of these axes. Now if you notice, there are 3 points that are here, A, B, and C, and then those 3 points stretch AB, creating a vector AB, and then maybe AC or BC, whatever you want to use. So those 3 points are describing or pinning down 2 vectors. And by crossing those 2 vectors, you are going to get another vector which is orthogonal to both original vectors. Now there is a very interesting thing. A plane, which is this keyboard, detachable keyboard that I'm holding now, you see, if you have 3 points in space and you rest the plane on those 3 points, the plane is not wobbly at all. If you try to do that on 2 points, you see the plane is wobbly. You can have 4 points, 5, right? The plane is okay with any number of points that it's 3 or more. So the minimum amount of points that you must have to describe a plane in 3D space is 3 points. And those 3 points would give rise to 2 vectors that you can cross to find the orthogonal vector, which will be orthogonal to the plane. You see the 2 vectors, A, B, and AC, in this case, right? If you're looking at A, B, and AC, these 2 vectors are in the plane. And if you cross those 2 vectors, you are going to get an orthogonal vector. So, right here we are with AB and AC, okay? You all see that? AB and AC. Those two vectors, AB, AC, are enough for us to have a plane. As soon as you cross AB, AC, you are going to get orthogonal vector. Now that vector is always orthogonal. It's always 90 degrees in all directions to the plane. Now, no matter which way the plane goes, normal vector will always be orthogonal to that plane. Well, we can think of that normal vector as the carrier of this 3D slope orientation of the plane. Because it's very easy to describe a vector in 3D using 3 coordinates. And it's always orthogonal to the plane, as you can see. So if I know this, I am able to write a very easy equation for the rest of the plane. So that is the way we build planes in 3D that are not parallel or perpendicular to the basic planes that we have as XY plane and YZ plane and XZ plane. So we are going to, well, there is a definition. We're going to first copy the definition, right? And then we're going to use the cross product and everything else. So given a fixed point P0 and a non-zero and a non-zero normal vector n, lowercase n with the arrow on top, the set of points P in R3, this is the way to denote the third-dimensional space, for which P naught P vector is orthogonal to n is called the plane. Yeah, that's a lot of words. Let's take a look at a picture. What I have here is vector A, B, and I have another vector A, C. The cross product of vector AB with the vector AC is going to give me a vector n. That vector n is orthogonal to the plane and in some sense carries its slope. Notation now is that vector n has this, it's not a unit vector, vector n has the coordinates a, b, c. And you know how to find this vector simply by using cross product. So now we can write general equation of the plane. It says ax minus x0 plus by minus y0 plus c z minus z0 equals 0. Now, the x0, y0, z0 is the p0 fixed point. And you already know that A, B, and C belong to the normal vector n. X, Y, Z have to stay there because that covers the space. So this is our general equation. For the plane. And then there is the other form. So, or ax plus by plus cz equals to d. When you distribute everything, you get this ax0, right? You get all of those. So d is ax0 plus by0 plus cz0, if you want to use it that way. Is this going? Yes. Okay, good. So we have now equation of the plane. Let's do the example right away. Find the equation of the plane passing through, let's have origin 1, 1, 2, and negative 1, 3, and 4. Yeah. So you have yourself 3 points. You can name these points if you want, A, B, C. It's fine. Do not confuse it with a lowercase a, b, c. Maybe you can call this P, Q, R. You can create a PQ vector, which would be clearly 1, 1, 2, because you're subtracting 0, 0. And you can also create a PR vector, which is going to be negative 1, 3, and 4. So this is what we have for our two vectors. Now to create a plane, we cross these two and that gives us n, and we use 0, 0, 0 in this case as a fixed point because the vectors emerged from that point, right? So we use now the cross product, n equals PQ cross PR. If you remember, you have your I, J, K unit vectors, then you put the first vector 1, 1, 2 and the second vector negative 1, 3, 4. And then you grind through the cross product, which is the procedure which you must know, right, in Calc 3. So this one is 4 minus 6 negative 2. This one is 4 plus so is 6 negative 6. And the last one is 3 plus 1 is 4. So that should be the normal vector once you do your cross product. And once the once you have the normal vector, we just now write out the equation. So the equation is A x minus x0 plus B y minus y0 plus C z minus z0 equals 0. Alright, great. I have my A, B, C, that's the normal vector, and I have my fixed point over here 0, 0, 0. So no yawning. So for A, I have negative 2 x minus 0 minus 6y minus 0 plus 4 z minus 0 equals 0. What is the plane? In this case, negative 2x, negative 6y, plus 4z equals 0, and that will be the answer. So you make your vectors, and you just do the cross product, and you arrange everything inside, and it's it. It's a, dare I say, straightforward procedure. So now when you have these, when you have a plane, you see that it's completely described by these two features, normal vector and the fixed point through which it goes. So all you need to do is to plug in normal vector and a fixed point everywhere where they belong, and you're done. So just plug in. Now we can clearly have a lot of other cool things that we can consider here. First off is we know that the cross product is not commutative. But we know that the vector we get when we swap the order in a cross product is negative. Now observe the fixed plane in space. And here is your, let's say, u cross v, and here is your v cross u. You see that? It's the same vector, has the same direction, same magnitude. It's the opposite direction because of the negative. Cross product simply gives you the one that looks down or the one that looks up. And it doesn't matter because all of the signs are different, and in the equation it's equal to 0. So you can multiply by -1 the whole thing. When you multiply 0 by -1, it doesn't change. All of these signs will change. So it doesn't matter in which order you cross those vectors at all. So I could have, right, clearly if I multiply this by -1, it's going to be 2, 6, -4. That's completely opposite here, right? Which would be PR cross PQ, the other way around. So now we know how to find the plane. We also know that it doesn't matter which of the normal vectors you use. There we go. Now, look at this surface. Do you see the plane over here on top? And you see another plane in there? What's the angle between them? Right? What's the angle between the two planes? Or here, doesn't matter. Oof. Yeah, I know. That's how we do the engineering. Just eyeball it, right? So yeah, it's good now. Guess the third decimal. Imagine anything constructed that. Well, a lot of things are constructed that way. That's why it's falling apart. But we can find that easily. If you intersect two planes, each one of them has a normal vector. And what do we know if we have two vectors? What can we do to find the angle between them?
You know, they take this dot product.
Dot product, and you have your beloved cosine, right? So let's see if I it's one plane. Just want to intersect two planes here. So these are the planes intersected. No! So two planes are intersecting now. And what I'm going to do is I'm going to draw two normal vectors. There is a normal vector going this way. Normal vector 1. And there's a normal vector this way. Normal vector 2. The angle between the two over here, call it theta, is the same theta that it's the angle between the two normal vectors. So instead of me working with planes, I can just pick off their normal vectors from the equation and use the dot product formula to find the angle between the normal vectors, and you get the same angle between the two planes. And then you can start constructing this stuff. So when I have a x minus x0 plus b y minus y0 plus c z minus z0 equals 0, these guys over here create a normal vector 1, ABC. Get normal vector 2, alpha, beta, gamma. Alright, so you have two vectors now. And now just use theta equals, can anyone tell me, help me? I don't remember this stuff. Very good. Dot product between, yeah, you guys, I mean, you're amazing. I know. It's amazing. So you can find the angle between two planes by simply reading the normal vectors. Now, you can also find the line of intersection here. The two planes intersect at the line. So this will be to get the angle. Now, let's see, what else can we use? Just a little black. How about, choose purple? Purple. To find the line of intersection of two planes, use the cross product. Well, that should be common sense. The cross product of two normal vectors is going to give you a perpendicular vector which is parallel to the line of intersection. They're all 90 degrees, 90, 90, 90. Are you having a problem with this visually? In the corner, right? As soon as you look at the corner of the room, it must be clear. Or ceiling, I don't care. What is the normal vector from the ceiling? It's a vector pointing straight down. What is the normal vector pointing from the wall? Pointing towards you. They intersect at the 90 degrees, right? Over here. When you cross those two, you will get the vector that goes this way, which is parallel to the the line you're looking for. So you can quickly come up with those things when you just need to look around, because you live in a 3D space, and all of these things need to make sense quickly if you think about it a little bit, right? So the cross product of this is parallel to the line of intersection. Now, that is your V for R of t equals Vt plus R0, if you still remember that formula, because we're looking for equation of the line. Now, yeah, you can go and you can put your x, y, z, and then, now don't confuse ABC of V with ABCs of n's, because they're not the same. You see, we run out of notation very quickly in this class. So to find the angle between two planes, just use the dot product with other bells and whistles, obviously, to find the angle between the two normal vectors. And then to find the line of intersection, use the cross product to find the V. Remember that vectors are free to move in space. So even if the line coming from here, right, and the line coming from here, they may be intersected here, when you get your cross product, it's going to be the vector which you can just move in a corner. You can put it anywhere, as long as that vector will be parallel to the line of intersection of the plane which is ceiling and a plane which is a wall. So that's about planes. You need 3 points to describe a plane, right? 3 points to describe a plane. And once you put the plane on a 3 points, it's not wobbly. If you use 2 points, as you can see, it's wobbly. If you use 1 point, it's really wobbly, right? But as soon as you put 3 points, that's the minimum that you can have. Anything more than that is okay. You can have 15 points as long as they all lie in the same plane. They belong to the same plane. And then we know that we can stretch vectors between those 3 points. You can cross those to get vector n. And then we can finally write the equation for the line. And then do some examples. Now, life is not only about planes. We also have curved surfaces. For instance, this thing is a combination, this correctional behavior device. See that? Oh, it twitched. If you look at this, we have a cylinder over here and some type of a funnel. Call it a cone. It's not, because it's, cone should have a straight line. This has a curved line. But call it a cone. I don't care. So this would be a combination of few shapes. So we do have mathematical functions, right, that we can use to describe these shapes. We start obviously first with the simple ones. The simple one would be the cylinder. Cylinder meaning it's also like a pipe, right? So cylinder. So cylinder is this. Now, you are used to some of these shapes, cone. pyramid. Three-sided pyramid. Whole bunch of prisms that are, you know, rectangular shape like this. They don't have to be regular, they can be highly irregular, right? So there are all these 3D shapes that we are going to use, especially in chapter 13. Now, we also have shapes that you can get by extending the two-dimensional image in a third dimension. For instance, if I take a two-dimensional shape parabola, and this is on xy, I want you to think about me taking a piece of chalk and drawing parabola on the floor. So where's my third dimension? I'm going to take a piece of paper and fold it along whatever I drew on the floor, and then it's going to sit. It's going to be a parabola that you are all used to, but it's going to sit this way on the floor, right? So technically, just by bending a sheet of paper and placing it on the floor, you have a trace of the parabola on the xy plane, and then z is going to extend infinitely because the paper is supposed to be infinite. Or I can limit the z from 0 to 8, right? 8.5 or 8? 8.5, yeah, thank you. 8.5. So cylinder, in this case, is just a much broader shape name. It's not just this. That was also cylinder. So this particular shape, I can either just leave it be y equal x squared. It's still three-dimensional because it lives in 3D, and because there is no mention of z anywhere in the equation means that z extends infinitely in straight line fashion, right? But then, if I want to limit this and have a finite sheet, I have to provide some restrictions, and restrictions will be 0 to 8.5 on z if I want the finite shape. It's like dealing with line segments. So I am able to build up 3D on top of 2D by simply building on top of this line. Can anyone tell me an application for something like this when you take a look at the 2D contour and then build up 3D from there?
They use it on Inventor. The software, you can...
and what is it for?
You can build a shape and then you can bump it out to 3D in Inventor.
Yeah, but for what? What is the Inventor?
Building shapes like boxes.
3D printers, thank you. Yeah. Right? So if you ever seen a 3D printer before, if you want to create this type of a shape made out of plastic, the 3D printer is going to just keep drawing parabola on top of each other, right? Parabola, 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 parabola. It's going to go back and forth, back and forth, back and forth, and actually build it on top. And you will actually be able to see those layers of plastic that are stacked on top. Now, this is where I need a 3D printer in Calc 3 in classroom, so that by the time I finish the lecture, it already printed ½ inch of a stack. Which is the reason why we don't have a 3D printer in classroom, because it will take forever. And someone will play with it and break it. Good. Now, a very powerful technique for you to visualize these objects is trace. You should think of a trace as a cut through the object. So when I have an object, and I'm going to make out of this piece of paper a cylinder, so you are thinking about your soda can or whatever. If I am to cut the object, either with the y plane or with the x plane, I will just see a rectangle in a cut. Think of it, right? If I am to, so we're thinking of the cylinder only. If I'm to cut this way in the middle, all I'm going to see is this straight edge and this straight edge and this straight edge, right? So if I have a cylinder, and I cut that cylinder, this way, all I'm going to see is the rectangle. If I have the same cylinder and I cut on x-axis, I am also going to see the rectangle. So this is the y-axis cut over here, and this would be the x-axis cut, right? Well, I can also cut on z, which is just going to cut in half, right? Take a plane z equals 3 inches and just cut through it this way. You are going to see what? A circle, exactly. So if you are able to put these shapes in your head together using the trace, Calc 3 should not be too much of an issue. And this would be the Z cut. Because you cut at Z equals 3 or whatever. So if this is Z equals 0 and Z equal, let's say, 6, then over here we cut Z equals, you can cut Z equals 1 or 1.83, I don't know, whatever. But we see that it's a Y cut. So what do you have? If you like ninjas, like I do, that was a dream. And then I ended up doing this. Oh. So awesome. Anyway, so you can cut the X way, the Y way, and the Z, right? With a sword, for instance. We are going to call these cuts trace. And the trace is going to be, when you cut along y-axis, it's called the xz trace. And then yz trace. And xy trace. You can also think about it, what kind of shadow would you get if you are to shine the light, and swords work the best. All right, swords work the best. And there are other shapes that they cut in the book, so you can take a look at those. Now, just to get these cuts, it's very simple. You just say, okay, I want to cut at y equals to 3. I want to cut at y equals to 0. I want to cut at z equals to 0. Right, so you see me over here cutting with z equals 3. That's the elevation. So we can cut this classroom in half by taking a huge sword and saying, cut at z equals 6. And then all of us who are over 6 have an issue in that case. And those of you who are shorter than 6, you're safe. All right? And the last part of this lecture is the part on quadratic surfaces. And the quadratic surfaces are interesting creatures. People say, oh my, do I really have to memorize these equations? Well, if you already know some stuff, these equations are not an issue at all. Take a watermelon, for instance, as an example. All right? The shape looks more like an egg over here, but it's a watermelon, okay? So the shape of the watermelon here is known as ellipsoid. If you take a sword and you take the watermelon and you cut any way you want, you always get an ellipse. Make sense? It should make sense. So, you put the watermelon and you cut through the middle, and the trace is ellipse. Take another watermelon and you cut straight down. It's going to be again ellipse. And if you cut 90 degrees, ellipse again. So no matter which way you cut the watermelon, you can cut this way, you can cut along the way. No matter which way you cut, there are three cuts that you can make: XY cut, XZ cut, and YZ cut. So the three cuts, every time it gives you. So now it's going to be called ellipsoid. And if you look at the equation for ellipsoid, x squared over a squared plus y squared over b squared plus z squared over c squared equals to 1. This should make sense. When I cut at the z level, so I'm cutting xy plane, horizontal, right? When I cut with the xy plane, z equals 0, this thing over here dies, and what's left? Equation for the ellipse. If I cut with y equals 0, that term dies, what's left? Equation for the ellipse. And x equals 0, again equation of the ellipse. Anytime you cut with a trace, if you're not cutting with the basic planes x equals 0, y equals 0, z equals 0, you are cutting with z equals 10 or y equals 10. It doesn't matter. There are still going to be ellipses, no matter where you cut. It's ellipsoid. Any cut on it is an ellipse. And that is preserved in the equation. I know we're over time, so I'll do one more, and then we'll take a look briefly at the rest on Wednesday. So here is the elliptic paraboloid. This is elliptic paraboloid. Why is it called elliptic? Aren't all of these ellipses? Anytime you cut with z, you get an ellipse. Even if this is a circle, circle is a special case of the ellipse. So anytime you cut through z, you get ellipses. Anytime you cut with the x and a y, you are going to get, so let's cut x. You are going to get parabolas. See, if this is x cut, see it goes like this, and then isn't this parabola? Yes, it is. And now cut y. Y cut is this way. Let's use blue for a y cut. If you use the y cut, you just have the parabola that you actually can see. And if you use this one, z cut, you get the ellipse. So now, what would be the common sense equation for this? Let's build it. I know that y equal x squared to give me a parabola, right? I also know that when z is out of the picture, I have to have x squared plus y squared over a squared and b squared, right? I have to have that equal to 1. But then I realized that this is not a y, this is a z, because that's a z-axis for parabolas. And then it's a zx and a zy. Great. Just fix this. Done. So let me check. Let me check. If I'm cutting with z equals 0, then this thing is equals 0. Then all of this stuff is equal to 0, and that only happens when all of the stuff is 0 here, so I'm getting a point. Nice. That's a 0, 0, 0 point if I'm cutting with z equals 0. But if I'm cutting with z equals to 10, okay, well, now this is equal to 10, and that's an ellipse. Great. That's exactly what I have on top over here, let's say, right? Now let me cut with x equals 0. If x is equal to 0, hey, is equal y squared. That's a parabola. And if I cut with y equals 0, z equals x squared, that's a parabola as well. So I see the two sets of parabolas, x squared z parabola and y squared z parabola. And then I also see what x squared plus y squared equals 1 for my ellipse. If these guys are the same, it's a circle, right? So we still call it elliptical, right? Because it is, circle is a special case of ellipse. This is the way you build this and you understand these formulas. You have to sit. There's nothing I can teach you. I'm sorry. That's the end of the end of the talk. Because if you are not going to sit down and use your finger to cover parts of the equation and look for the shape that the trace will give you, you will probably not figure this out. Because you shouldn't. You have to sit and analyze each one of these so that you can see, right? And then I will go through there are 4 shapes left. I will go through the other 4 shapes next class. It will not be on a stream, right? But it's going to be the same story like this, me covering parts of the equation and talking about, okay, now you see the trace is equal to so and so. But I highly encourage you to start working with this because, guys, integration is coming. Chapter 13. And guess what you're integrating, right? So now I have to see these shapes in 3D because we are looking for those volumes, all right? Or the characteristics within the volume. Because if you integrate function, you get 1 dimension up, which is area. If you have a triple integral on a function, how many dimensions do you get? Right? So that's going to be your 3D shape plus whatever characteristic is in it. Temperature, density, right? Or whatever else. So we're going to talk about those things in chapter 13, but this is your prerequisite knowledge, right? Knowing what the shapes and how to bound the shapes and so on. See you all in 2 days. Ciao.